What's up, Precalculus? This is lesson 2-4, zeros of polynomial functions. And this is a long section, so we're going to try to get through it here as quickly as we can. The first key concept is the rational zero theorem. It just says if you have some polynomial in its general form, it says that all the rational roots, meaning all of them that can be written as a fraction, are factors of the constant term and that leading coefficient. So with p over q. So p is some factor of the constant, and q is some factor of the leading coefficient. So do a ratio of those, including positive and negatives. Those will be the factors. So here's an example. Here's this guy practice 2a. 2x cubed, blah, 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 minus 36. So I just need to find factors of this 36, 1 and 36, 2 and 18, etc. Factors of this leading coefficient 2. So I'm going to list all the possible factors here. It's going to be like 36 over 1. I'm just going to go through this list over here, dividing by 1, which is just, so I'm going to say plus or minus 36, plus or minus 18, plus or minus 12, plus or minus 9. You get the idea. Now we're going to go through this list a second time, but now using the 2 as my denominator. So 36 divided by 2 is 18. I already have that one. 18 divided by 2 is 9. I already have that one. 12 divided by 2 is 6. I already have that one. 4 divided by 2, I already have that one. 3 divided by 2, so it's going to be plus or minus 3 over 2. 2 divided by 2, I already have that one. And then I'm going to have plus or minus 1 over 2. So this is all a list of them. Then I would go through and check each one of those 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 22 different ones using synthetic division or direct substitution and check them. Now, is that really long? Yes, it is. I agree with you. However, if I didn't have this list, I'd be checking infinitely many different ones. And we're going to be working through this section to see how we can reduce this number smaller and smaller. The first way to reduce that is if you had an upper or lower bound. Meaning, if I have this whole list on mine that went somewhere from positive 36 all the way to negative 36. What if I had some lower bound, I'll call that A, and some upper bound, I call it B, that I said, hey, I know all my zeros are going to fall in between these two numbers. That means I could kind of take out all of these above and below that. And that's what this key concept here is with upper and lower bounds. It says, let f be a polynomial function of degree n bigger than or equal to 1. Real coefficients, positive leading coefficient. Suppose f is divided by x minus c using synthetic division. Okay? If c is less than or equal to 0, and every number in the last line of division alternately non-negative and non-positive, then c is what we call a lower bound. If that c is a positive number, and every number in the last line of the division is non-negative, then c is what we call an upper bound. So let's kind of just try one of these. It says determine an interval in which all real zeros of the given function must lie. Explain your reasoning. Then find all the real zeros. So right now we're just going to do this first part here of determining that. The first thing I'm going to do is I'm just going to throw this into Desmos or into a graphing calculator, and I'm going to find out, just estimate, what do I think is a lower bound? Well, I'm looking on here, it looks like these are going by 2s, 2, 4, 6, 8, 10. So I'm going to say an upper bound is over here at 2. And a lower bound, I'm not sure if negative 12 is, so I'm going to say over here, negative 13. Okay, so I'm going to say that's going to be my lower and my upper bounds. It should be everywhere between there. Now let's check that real quick. 4, 3, 2, 1, 0. So over here, I'm going to put that negative 13 to see if it's a lower bound. I'm going to have 6, 70, negative 21, 35, negative 12. Okay, so I finished this out for you. Notice this one is negative, this one's positive, this one's negative, this one's positive. Since those are alternating, non-negative and non-positive, which means they could be 0, that's okay. Since these are alternating, that means this is indeed a lower bound. Try this one more time with the upper bound. So I'm going to say 2, etc., etc. Looking through this, notice all of these are staying, they are non-negative. All these are non-negative, meaning they're 0 or positive. So since those are the cases, is indeed an upper bound. All right, now Descartes was a French mathematician and scientist, etc., who discovered this pattern in being able to determine the number of positive real, not just rational, but the number of positive real ones, the number of negative real zeros. And we could do that just by looking at sign changes. So it says the number of positive real zeros of the function f is equal to the number of variations in signs of my function, or less than that number by some even number. So looking here at this one, notice this is positive, this one's positive, and this is negative. So notice here, this is one sign change, and then from here to here is negative as well. So how many variations in sign do I have? Just one. So if this number was, say 3, it'd either have 3 or 1. But since it's just 1, I just have one positive. When we do something similar, if we want to see the negative real zeros, we just have to plug in negative x. Thankfully for you, I already did that. I plugged in negative x into this function. I got this. Now I need to see how many sign changes I have. Well, it goes from negative to positive, so there's 1. Positive to positive, that's not another 1, but from positive to negative, that's 2. Well, one more, making a total of 2. So for negative zeros, I either have 2 or I have none. Alright, now this next theorem is pretty important because they specifically say the fundamental theorem of algebra. So this is the fundamental theorem of algebra. I think we've talked about this last year in Algebra 2. We're going to talk about it again right now. The fundamental theorem of algebra says a polynomial function of degree n, where n is bigger than 0, meaning it has at least degree 1, has at least one 0, real or imaginary, in the complex number system. But then the corollary is really where it gets amazingly awesome. It says a polynomial function of degree n, meaning if it's a quadratic with degree 2, has exactly n zeros. So if it's a quadratic, if there's degree 2, that means it's going to have 2 zeros. If it's linear, it's going to have 1. If it's a cubic, it's going to have 3. Now that does include repeated zeros and complex numbers. But if that's the case, so if it's a 5th degree, that means I'm going to have 5 zeros. If it's a 4th degree, I'm going to have 4 zeros. So once I find those 4, I don't have to keep looking because I know exactly how many I'm going to have. Now also based on that is a linear factorization theorem, kind of stems straight from this. It says if this function has degree n, then that means there are n linear factors in this. And so that kind of makes sense, right? If 2 is a 0, that means I'm going to have x minus 2 as a factor. If I have 7, then I'm also going to have x minus 7 as another factor. So those kind of correspond together. Notice I do have that a sub n there as my leading coefficient if you want to get fancy with that. There's also, we talk about complex conjugates, or the conjugate root theorem. It just says that if we have a complex number a plus bi, where that b is not equal to 0, then its complex conjugate a minus bi is also going to be a root. So that means if this is a root for plus 3i, this one will be as well for minus 3i. That's the complex conjugate of each other. If I have 2 minus I, that means 2 plus I is going to be 1. If I have negative 6I, I'm also going to have 6I as factor because these are complex conjugates of each other. So it says write a polynomial function of least degree with real zero coefficients in standard form with the given zeros. So right here, I have a negative 3. So that means I'm going to have this factor. I'm going to have x plus 3. Because if I plug negative 3 into that, that would make it 0. Since I have 1 as a factor, I know x minus 1 would be a factor of that. And notice it says multiplicity 2, which means I need to square that one. And then the next thing it says, I have 4i. So that means I'm going to have x minus 4i as a factor, because if I plugged 4i in for x, that one would be 0. But since we have that complex conjugate rule, that means I'm also going to have a negative 4i also as 1. So I'm going to say x plus 4i. So this is kind of the basic one, but they want it in standard form, so I'm going to need to expand that. I'm going to go and multiply those two together. Notice that this term and this term go to 0. Remember that I squared is equal to negative 1. So this is going to simplify down to x plus 3, x minus 1 squared. This is going to be x squared plus 16. Expanding that one, we get this. Multiplying this and this together, we get this whenever I go shoo, shoo, shoo. And same with the 16. I can combine this plus and this. And then finally, I need to multiply this by everything in there. X times each of those gives me this line. 3 times each of those gives me this line. Now I just got to combine each of those. And my final product will be, well, pow. Notice we had 1, 2, 3, 4, 5 zeros. And what's my degree? 5. So this would be my polynomial of least degree that has these zeros in it. Now for this one over here, we're not going to go all the way through because that's going to take forever. But I'm going to have an x minus 2 square roots of 3 from that one. I'm going to have an x plus 2 square roots of 3 from that one. I'm going to have an x minus that thing, 1 plus I. And then because this is complex, I'm going to have its conjugate of that. So I'm going to say x minus the conjugate, which would be 1 minus I. Now, in an effort to save time, like I said, I am not going to multiply this all out. This looks kind of messy, but if I multiply this times this, that'll work out a lot nicer because you'll get rid of those roots, square roots in there. Multiply this by this, I'll get rid of my i's. I'll go and simplify this down here just a little bit so you can kind of see what that looks like. This would be x minus 1 minus I times x minus 1 plus I. And again, whenever you multiply those together, your i's will kind of reduce out there and it will get a lot nicer for you. Alright, so this is kind of the last thing we're doing, and it will take a little bit of time, so just bear with me. But we can do this. It says, for each function, use the given 0 to find all the complex zeros of the function. Then write the linear factorization of the function. So really what we're trying to do is we're trying to factor this all out. We're trying to find all of its zeros. And we're trying to write it in its factored form. Thankfully for us, they did give us this 1, 0 right here. Okay? And since this is degree 4, we know that we need to have 4 of them. Also, because this is an irrational root, we also know we're going to have this one, 2 plus square roots of 3. 2 minus the square root of 3. Okay, but here we go. Let's, since we know this is a factor, let's put that over here. 2 plus the square root of 3 is going to be 1, negative 10, 35, negative 46, 10. 1, this is going to be 2 plus the square root of 3. Subtracting 10 is going to give me negative 8 plus the square root of 3. This is where it starts to get a little bit more complicated. So I just FOILed first, outer, inner, last. The square root of 3 squared comes out to be just 3. So negative 16 plus 3 is negative 13. 2 minus 8 is the negative 6 square roots of 3. So that comes up right here. Negative 13 minus 6 square roots of 3. Add 35 to that. Then multiply this times this. That goes right there. Feel free to pause it and look through this. But I got 26 plus 10 square roots of 3. So I'm going to go right here. I'm going to write it 26 plus 10 root 3. Minusing 46 from that's going to give me negative 20 plus 10 root 3. Multiply this times this, and I put it right there. Again, feel free to pause and look through that right there, but I got a negative 10, which goes right here. 10 minus 10 comes out to be 0. Now, what did that just tell me? Well, it just told me that this right here that they gave me is indeed a factor. Okay? Well, thanks, Mr. Siri. We were already told that. All right, but what this also gave us was a reduced down polynomial. Here's 1, here's 2, here's 3. So this is going to be my constant. This is going to be my x term, my x squared term, and my x cubed term. Now what I can do is I can go ahead and do this again, but with my other factor, and that will tell me another reduced fraction as well. So I'm going to go ahead and try to do this one more time. So here's my setup. I'm just using this conjugate of this. I'm just using these last terms here for these. 1 is going to be 2 minus the square root of 3 because I multiplied this by 1 to get this. Whenever I add those together, negative 8 plus 2 gives me negative 6. That's a positive square root of 3 minus square root of 3. It goes to 0. Whenever I multiply negative 6 by this, I get negative 12 plus 6 square roots of 3. Lucky for me, whenever I add those, go to 0. 22 minus 12 just gives me 10. And then whenever I multiply this by this, I'm going to end up with 20 minus 10 root 3. Negative 20 plus 20 is 0. 10 square root of 3 minus 10 square root of 3, that's 0. So my remainder is just 0. Okay, so what does this tell me now? Well, this is an x squared minus a 6x plus a 10. This I can factor, and we'll do that more in a second. I also have this x minus the 2 plus the square root of 3. And I have the x minus 2 minus the square root of 3 as a factor. All right. This part doesn't factor because there's no factors of 10 that add up to 6. So I'm going to go ahead and do the quadratic formula over here, which tells me x is equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. That gives me 36 minus 40, square root of negative 4. This is going to give me 6 plus or minus 2i all over 2, which is equal to 3 plus or minus I. So my zeros are 3 plus or minus I, and also 2 plus or minus the square root of 3. Written in factored form, it's going to be like this: x minus 3 plus I, x plus 3 x minus, 3 minus I, and then those two, which I can simplify down to be x minus 2 minus the square root of 3, if I distribute that in, and x minus 2 plus the square root of 3. Doing something similar here, this will be my final answer here. It's going to be x minus 3 minus I, x minus 3 plus I, and these from up here, x minus 2 minus the square root of 3, x minus 2 plus the square root of 3. So that is my factored part, and those are my 4 zeros because my degree is 4. Whew. We survived. Your homework is a worksheet. Make sure you get that, and good luck, guys. You're going to do awesome.